right. Good morning, grade 12s, and welcome to the new year and the last few weeks of our semester. I hope you all had a fantastic Christmas and New Year's break. Mine went very well. We had our little baby. She was born on December the 30th, and her name is Layla Marnie Porcelato. So things are going really well. I'm just going to be at home today, tomorrow, and I'll likely be back. I'll definitely be back before the end of the week. So I'm just taking a couple days to stay around and help out around at home for before I get back. Um, so for the days that I am away, I will just be recording the lessons. They will be posted. Okay. I will try to have the lessons posted the night before. And again, I'm not going to miss. Won't be missing lots of time. But if I am going to be away today and tomorrow, so I will post tomorrow's lesson at some point tonight, so that if you do want to go on and watch it beforehand, you can do that. As for, I know before the break, we had our logarithms test. I know there's some students who will be writing that today. The supply teacher will have access or will have those. So if you do have to write today, those should be, you should hopefully be started. Just to quickly go over for the volume, if you're having issues with the volume, just hit the little speaker down here, and there will be an option if you're having trouble getting into the speakers. Select the speakers and just change the output for the audio. So hopefully that works and you can all hear me at this point. Okay. So I know before the break we talked about, the test took slightly longer. Most people finished. I've taken a look at a number of them and almost marked most of them. So for the most part, students got most of the questions done. There were just a couple questions here and there that maybe some students didn't get done. So after speaking with Miss D'Amato, what our plan is going to this unit is a short one. It's only 4 lessons. And for our unit test, because this unit actually looks at characteristics of all functions, okay, it kind of encompasses all the types of functions that we've been looking at, which is why we've saved it to the end. What we're going to do is we're going to make the final test for this unit, which will be done next Monday or Tuesday. The final test for this unit will be kind of focused and centered on the log functions. So this is a new unit, but this test will be an opportunity for you to also improve your log test mark, because the questions on this will be centered around log functions. There will be a couple questions about other types of functions, but for the most part, this test will be log centered, okay, for the topic that we're looking at. And then we will include a bonus question on this test from our log unit. Okay, so there will be an opportunity for you to also answer a question about a topic from our previous log unit, and that will be included in your mark for your logarithms test. Okay, so that's going to be our plan for this unit. And for kind of, if you didn't get your entire log test finished, like I said, this will kind of be an opportunity to kind of improve that mark, show us what you know, and move forward with that. Okay, so that's going to be the plan. This lesson is not a very long one. And the topics covered over the next 4 days are kind of they're very similar ideas. Okay, so I'm going to start today by talking about rate of change. Okay, so you see here we have slopes of secants and average rate of change. So that's going to be what I'm going to talk about first, and I'm just going to talk about slopes and average rate of change in a sense of what you would have done in grade 9 and grade 10. We're going to take a look back at what exactly are slopes, what is rate of change, and then what we're going to do is we're going to apply that to some functions that we've looked at in this unit. Okay, or sorry, in this course. All right. So I'm going to just start over here. And I'm just going to pause for just a moment and then I'll continue. So let's see if I can pause here. All right, sorry about that. So what we're, like I was saying, what we're going to do is we're going to start by just looking at what is slope. Okay. What is slope? All right. So, and you don't need to write this down. This is kind of just going to be a little bit of a recap, just to remind you of what exactly slope is. Now, in grade 9 and grade 10, you would have looked a lot at lines, right? Straight lines, or what we call linear functions. Okay. Now, a linear function, we can say that, is the slope of this line changing? Is it changing? Is it constant? Or is it changing or is it constant? Right? And the slope of this line is constant. Okay. The slope of a straight line is always constant. Okay. So our slope of this line is constant. It's not increasing or decreasing throughout the domain. Okay, so we say that the slope of this line is constant. And all that means is that if I pick any 2 points on this line, so maybe I pick these 2 points here, and I determine my rise and my run, and I pick 2 other points, maybe here and here, and I calculate my rise and my run. What a constant slope means is that your rise over your run will always be equal. Okay, no matter where we measure along this line. Okay, so our rise over our run on this line will always be equal no matter what 2 points we select, because this slope is constant. The slope is always the same. Another word for slope, right? Slope is the same as we can call it steepness, right? Slope has another term that we use a lot and that we're going to use a lot in this unit, and that's rate of change. Let me make sure my spelling's correct. Right? And what rate of change means is it means the rate at which our y values are changing in respect to our x values. Okay? The rate at which your y values change for every increase in our x value. Okay? That's what rate of change means. It means how fast or how slow is our function changing. Okay? And again, so we've kind of talked about slope, right? We see what slope is in a straight line. Our slope is constant. Okay. Slope, we can also refer to it as steepness or rate of change. And we know from previous years that slope is equal to rise over run. Okay. So what we're going to look at here just quickly is we're going to look at the equation for slope. Okay. So you would know, okay, or maybe recall that slope is equal to rate of change, right? We have those 2 terms. We can also say, and sometimes we might say, and you'll see maybe this term more this semester, but rate of change can be written as short as ROC or ROC, rate of change, or ROC. Okay. Now we know that slope or rate of change is equal to, and this is an equation that you would have looked at in the past, is equal to y1, y2 minus y1 over x2 minus x1, right? That's how we determine our slope. So if we kind of go back to my function right here, let's actually put some numbers in. Let's take a look at this as an example. Let's say this point here is 10, 5. And let's say this point here is negative 2 and, negative 2, negative 4. Negative 2, negative 4. Okay? So if I want to determine the slope of this line here, I would put in my y2. I would label my points. So I typically like to label my points. So this is my y2, y1. Oh, no, sorry. Y2, x2, x1, y1. Okay? I'm just going to pause it just for a moment. I just have to go get my dog. I'll be right back. Okay, so if I want to calculate my slope here, I would go 5 minus negative 4 over 10 minus negative 2. So my slope of this line would be 9 over 12 or 3 over 4. Okay? That would be my slope of the line. That's how we determine it. Now, we can also write this. We can also write slope. So basically what slope is slope is the change in y divided by the change in x. Now, this, and I'm not sure if you've seen this before, but this here, the triangle means change or difference. Okay, the change in y over the change in x. How much is my y changing? How much is my x changing? So from y2 to y1, in my example, it changes by 9. It goes up 9. And in my x2 to x1, it changes by 4. It goes over, 12. It changes by 12. It goes over 12. Okay, so change in y over change in x. So that's another way to write your slope formula. Okay. There's also another way to write our slope formula, right? And what I'm going to do here, I'm just going to put this up here. But if I want my y, right? If I want to know what my y value in an equation is, okay? How do I determine my y value in an equation? Well, my y value in any function is equal to f at the corresponding x, okay? So if I, for example, in this example, if I want to find what my y2 is, if I know what the function is, what I would do is I would sub in x2. So if I want to find my y2, I sub in x2 into the formula. And if I want to determine my y1, well, I would substitute x1 into whatever my formula is. Okay? So we can also write, there's another way to write this formula. And another way to write our rate of change formula is to write f of x2 minus f of x1 all over x2 minus x1. And all this is f of x2 is just y2, and f of x1 is just y1. We're just writing it in function notation. Okay? Now, this formula that you see right here, the last one that I did there, is a formula that we're going to be using throughout this unit. Okay? F of x2 minus f of x1 all over x2 minus x1. And all this formula is it is a different way of writing your slope formula from a few years ago. Okay? All right. So what we're going to do is we're going to take a look over at our note now. Okay, so I'm going to scroll over here. So when we talk about, well, first of all, when I talk about rate of change of a linear equation or a linear function, we know that our rate of change is always constant. So I could pick any 2 points and figure out my rate of change, and it's always going to be the same. However, when we're looking at, in this course, we really didn't look at linear functions at all. We looked at functions that were mostly nonlinear. Okay. And what that means is that in those types of functions, in nonlinear functions, your rate of change is changing. It's always changing. Okay. It's very rarely constant. Okay. So what we're going to talk about today is we're going to talk about what we call average rate of change. Okay. An average rate of change is a relation in a relation or a function is the change in the quantity given the dependent variable, so y, divided by the corresponding change in the quantity represented by the x variable or the independent variable. And notice here how it says change in independent. That means that's triangle x, and change in dependent. That's triangle y. Triangle means change is the it's no notation to write change. So it's change in our y divided by change in our x. Okay? So we pick 2 points and we determine the change in y divided by the change in x. So the average rate of change can be determined by calculating the slope between 2 points given on a graph, on a table, or by using an equation. So you can do it by looking at a graph, by looking at a table, or by using an equation. Okay. And now we have a new term here. So basically, everything that we've talked about here so far, we have average rate of change, which is just a bit of new terminology. But otherwise, we're just talking about slope. Change in y over change in x. Y2 minus y1 over x2 minus x1. Okay. Now we have some new terminology here. A secant line. Now, what is a secant line? A secant line is a line that passes through 2 points on the graph of a relation. Okay, specifically two. Now, depending on the type of function, it may pass through more, but we are only focused on two. Graphically, okay, so as we can see here, we have a function, we have a parabola, and the red line is the secant line. Okay, this line here, oh, it says, sorry. This line here is the secant line, the red line. Okay, notice that it passes through 2 points on the parabola. So we call that the secant to the function. Graphically, the slope of the secant line is equivalent, so the slope of that line is equivalent to the average rate of change passing through the 2 points. So if I want to find the average rate of change, okay, because notice here, right? Notice that in this section here, and I'm going to trace it out, the baby blue section here, right? This baby blue section here, our slope is not constant there, right? As we go from left to right, it's getting steeper and steeper. So because the slope is not constant, we can't find the actual slope, right? We can't find the actual slope between those 2 points. So what we have to do is we have to find what we call the average rate of change or the average slope. And all we do is we pick those 2 points and we just calculate the slope of what we refer to as the secant line. Okay. So we'll scroll down a little bit here. So it says for a function y equals f of x. Okay. Right. Remember all y coordinates are equal to when we sub in our x value. The average rate of change over the interval x1 to x2 is this formula. And this is basically what I wrote earlier. Average rate of change is equal to the change in y divided by the change in x. From grade 9, that's y2 minus y1 over x2 minus x1. Now, we know that y2 is equal to f of x2, right? If I want to figure out what my second y coordinate is, I just sub in my second x coordinate. If I want to find out what my x or my y1 coordinate is, I sub in x1 into my equation. So f of x2 minus f of x1 over x2 minus x1. This is the exact same thing. That doesn't need to be written twice. And all that is change in y over change in x. And that's what we refer to as the slope of the secant. So average rate of change is equal to the slope of the secant line between x1 and x2. Okay? So we'll look at some examples. Now note here it says that average velocity, because a lot of times in this unit we might be looking at some distance time graphs, but average velocity is equal to change in distance over change in time. Okay. All right, examples, because why not look at some examples? Okay. So it says during the 1997 World Championships in Athens, Greece, Maurice Green and Donovan Bailey ran a 100-meter race. The graph below shows Donovan Bailey's performance during the 100-meter race. It says using the table of values, calculate the average rate of change for the 100-meter sprint. So it wants us to calculate his average rate of change for the whole 100 meters. Okay, well, this should be a distance time graph, right? So it says for average rate of change. So what we're going to be doing here is this is actually, and this is a little different, this is actually our x value. This is our y, okay? Because distance time graphs is x versus y. Now, I'm not sure why down here. Let me see here. Oh, no. Okay, no, we're going to go, no, we're going to keep that as, sorry for this example, we're going to keep this as x and y, time distance. Okay. Or actually, that makes sense. Distance time graphs, yeah, cool. I don't know why I made that mistake. Distance time graphs are time is on your x, distance is on your y. All right, little mistake there. Okay, here we go. So what I want to do is I'm going to figure out the average rate of change for the whole 100 meters. So my first coordinate is going to be 0, 0. And my second coordinate is going to be 9.77, 100. This is going to be my x2, y2, x1, y1. So all I'm going to do is, and I'm going to write A rock. A rock represents average rate of change. Okay. So my A rock is equal to, I'm going to just change my size of this. What is it? 100 minus 0 over 9.77 minus 0, which is equal to 100 over 9.77, or I just need to get my calculator out. Which is an average rate of change of 10.24 meters per second. Okay. It says calculate the average velocities. Okay, now remember, average velocities is the same as a rock between the following points. So it wants us to find between these 2 points and these 2 points. Basically, what we're going to figure out here is we're going to figure out, is he going faster or slower? Okay, is he speeding up or slowing down? So we're going to go A rock 1. So our first one, I'll highlight it yellow so you know the points that I'm using, is equal to. So this is going to be my x1, y1, x2, y2. So it's going to be 50 minus 0 over 5.44 minus 0, which is 50 over 5.44, which is 9.2. Or we'll go 9.19 meters per second. And if I want to find the average velocity between the other 2 points, again, I'm just using that same strategy here. So I'm going to go, let's just change that. I'm going to go my A rock 2. So my second average rate of change, and that's just going to be 100 minus 50 over 9.77 minus 5.44. This one here, if I just put that into my calculator, equals, divided by 9.77. Shoot. is 11.54 meters per second. Okay, so notice here that in the first, his velocity in the second half of the race is faster than his velocity in the first half of the race, which kind of makes sense because if you think about running a 100-meter race, at the start he's starting from a speed of 0 and has to increase his speed, okay, throughout the first 50 meters. So he's going to be going faster in the second 50 meters. It says compare Don Bailey's performance between the first half of the race and the second half. Well, he is running faster in the second half. Okay? So that's kind of our reason there. And you can see because it's a bigger number, right? Our velocity is larger. Okay, we're going to scroll down. We're going to just, that's what the graph looks like. Notice here that the scale along the bottom is not equal. So that's why it appears to be linear. Okay, our scale is not equal at the bottom. Okay, I think we just have two more examples. Okay. This question says, I'm just going to see how much time I have left here. Okay. What I'm going to do here is before I start the next example, I am going to pause this and get the second, because it's going to take me longer than 30 minutes, which is the max I can do for these videos. I'm going to pause this and then start part 2 of this video for the last 2 examples. Okay. All right. We'll talk to you on the second video.